So, good evening to everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. So, due to unavoidable circumstances, our regular class or regular discussion session, which was going to be held on the 25th of August, Sunday, from 3 p.m. to 5 p.m., and that has actually been preponed today from 6 to 8 p.m. So the reason, uh, uh, due to some personal reason, so this was done, and our next session after today will be on the 7th of September, same time from 6 p.m. to 8 p.m. 7th September, that is Saturday. Okay, Saturday 6 p.m. to 8 p.m. we will be having the next session after today. Okay, so in the previous class we actually uh, recapitulated the external stability criteria, right? First of all, we studied the external stability criteria. So what are the external stability criteria? What are the available external stability criteria that we have to check? That is the sliding check, the overturning check, and the bearing capacity check. These are the main three, and apart from that, we have to do the slip circle failure check. Okay, so these are the basic factor of safeties factor of safeties that we have to determine, and we have to ensure that the factor of safeties in sliding, overturning, bearing capacity, and your slip circle is more than the desired value. So these things constitute the external stability, right? These things constitute the external stability. Okay. So if you have any doubt, please interrupt me and ask me any question if you have. And apart from that, you can also type in the chat box if you have any doubts. Okay, and I will be responding to those. All right. So this is one thing. The second thing that we studied is the internal stability criteria. So what are the internal stability criteria? What are the internal stability criteria? If you remember, what was the internal stability criteria? You can even write in the chat box. Okay. What are the internal stability criteria? So mainly there are two main internal stability criteria. That is what? That is the tension, right? The what to say? The stability that comes from the what? Rupture, right? Stability that comes from the rupture, right? So we have to ensure that the reinforcement that we are going to use, that does not actually rupture, right? That does not actually rupture. That we have to ensure, isn't it? Right? That we have to ensure. Then next we have, apart from that, next we have the first is the rupture criteria. Second was what? The pull-out criteria, right? The pull-out criteria. So what was the pull-out criteria? Pull-out criteria is that the load coming onto the reinforcement should always be less than the frictional resistance that develops at the interface of the reinforcement and the what? The reinforcement and the soil, right? So the frictional resistance or the shear resistance should always be higher than the load that is coming onto the reinforcement, right? Else if the load is higher than the resistance, what will happen? The reinforcement will snap out or come out of the backplane, right? These are the two main internal stability checks that you have to ensure. Now, the third check that is there, that is the connection strength. Okay, the connection, the strength of the connection, the strength of the connection between the strength of the connection between the what, between the reinforcement, between the reinforcement and the what to say, the facing wall where the reinforcement is fixed, that should be strong enough, right? So that does not break, the connection does not break. Okay, so this is very important. So these are the three main internal stability criteria that we need to ensure along with the along with the our external stability, right? So first is the external stability criteria we have to ensure. Second is the internal. So now how will you ensure the internal stability criteria? How are going to ensure the internal? How are you going to like follow the internal stability criteria, satisfy the internal stability criteria? The answer to that is the spacing. Okay, the first is our what, internal stability, rupture stability, right? Rupture, we should not rupture, the reinforcement should not rupture. So to prevent that, we will space the reinforcement in such a way that the load coming onto the reinforcement is always less than the allowable tensile strength of the reinforcement. Okay, I will repeat again. The load coming onto the reinforcement should always be less than the allowable tensile strength of the reinforcement. Okay. And how are we going to ensure that? We are going to ensure that by choosing appropriate spacing of the reinforcement, appropriate vertical spacing of the reinforcement, or horizontal the spacing. So this will be done by the, so that rupture will be prevented by choosing the appropriate spacing. Okay, by choosing the appropriate spacing. All right. Now next is the what? Next we have a rupture. The next is the pull out. So what is the thing that will ensure that the reinforcement does not pulls out? The thing that is going to ensure that the reinforcement does not pull out is what? Is what? What is going to ensure that the reinforcement does not pull out? Please answer. You know that. We already discussed it in the previous class, right? So you should know this. So the thing that decides or controls the pull out or ensures that the reinforcement that won't pull out is the embedment length, right? The embedment length of the reinforcement beyond the active. So we need to calculate the embedment, right? So we will solve the problems and see how we do all these things. Okay, the basic so the basic thing first we have to do is that we have to ensure the external stability, and then we have to ensure the internal stability. So we'll solve some problems. So in today's class, in today's interactive session, what we are going to do is that we are going to solve only two problems. Okay, and those two problems will only take this 2 hour time. Alright, those problems are going to take time. So we will be solving only two problems, and the problems that we will be solving, those problems will be very simple, right? We can consider various loads like live loads, we can consider seismic loads, we can consider in the design, all these things we can consider, right? But all these loads we won't be using. We will be just so that conceptually the main basic, okay, so that the main basic concept is strong enough, so that the main basic concept is strong enough, we will be solving very simple and easy problems. Okay, very simple straightforward problems. Later what you can do, you can complicate those problems by yourselves by implementing seismic forces, right, seismic loads and all other stuff. You can do that. You can implement the seismic loads and all these things, and then you can resolve those problems again. But in today's session, what I will be doing is I won't be considering the seismic load and other stuff. Simply I will be solving all those problems, right? But what I suggest is that you please resolve these problems by whatever method or whatever way Professor Rajagopal has discussed in the main lecture classes. Okay, in the main lecture videos, however he has described everything, however he has solved everything, please try to resolve these problems using those methods. FHW standard methods. Okay, the Federal Highway Administration recommended methods and BSc British Standard recommended methods. So use those methods to actually solve those problems. All right, understood, right? So I hope you will be able to do that. Today, what we are going to do, we are simply going to solve the basic problems. Okay, basic straightforward problems. We won't complicate it. We will be solving basic problems so that uh, the main base is strong, right? The main base, your main concepts are actually strong. Okay, so next, so two problems we are going to solve. One problem is from the book by corner, and another problem we are going to solve, simple problem, that will be from by VNS book by V from the book by VNS. Okay, so these two problems will be solved. In the next class also we will be solving some more problems and we will see. Okay. Okay, so let us start slowly. All right. Okay. So please look into the problem. Read the question yourself once. Okay. Please read the question. So I will give you 1 minute. Just read the question yourself once before I read it, and try to think. Just try to think what is the information. Try to absorb whatever information that is given, and then think how can we use this information to do the required design. Okay. All right, so just read the question. I will give you 1 minute, 1 2 minutes. Just read the question. Okay. So what is asked? What is asked? Design a 6 meter high wrap around geotextile wall. So this is the first information. What is the first information? Sorry. The first information given to us is that we need to design a 6 meter high wrap around geotextile wall. So do you remember wrap around geotextile wall? How does a wrap around geotextile wall look like? Are you able to recall how a wrap around geotextile wall looks like? So a wrap around geotextile wall looks something like this, right? This is one layer of geotextile, and this is one more layer of geotextile, and more layer of geotextile. Like this, geotextile is built, and it is wrapped around. Okay, it is wrapped around. Like this, it is wrapped around. Right, like this, it is wrapped around. Hence, it is called a wrap around geotextile. These are the geotextiles. Okay, these are the geotextiles, and these are wrapped around. Okay, that's why it is called a wrap around geotextile. Okay, instead of using any facing or something, instead of using facing or something, what we do, you just wrap it around. Okay, instead of using facing, what we do, we just wrap it around. Okay, wrap it around. Hence it is called wrap around. Okay, so what is that? To design a 6 meter high wrap around type of geotextile wall that is to carry a storage area of equivalent dead load of 10 kPa. Okay, So dead load is given equivalent storage area. So above that it has some, like if this is the wall, so it has to carry some load. Well, some structure is there above it, and this structure is imposing a dead load of 10 kPa. Okay, okay. Well, the wall is backfilled with a granular soil, poorly graded sandstone SP, right? Poorly graded granular soil, having unit weight 18 kN per meter cube, friction angle 36 degree, cohesion 0. Okay, friction angle is 36 degree, cohesion is 0. A woven silt film geotextile. So this is a type of geotextile, a woven geotextile, silt film type. The silt film, if you recall the first class, you will remember first lecture that was given by professor, you will remember this, right? Yeah. Woven's, what is silt film geotextile? Okay, so a woven silt film geotextile with warp direction, ultimate wide width tensile strength of 50 kilonewton per meter. So there are two directions, right? One is the warp direction, and another is the weft direction. So say this is the, so warp direction was the geotextile is made in one direction, okay, in the machine direction. The machine direction is the warp direction, and the other, this side, other, so if this is the long, this side the roll is made, prepared in the machine. So this long rolling direction is the warp direction, and in the other direction is the cross machine direction, or the weft direction. Okay, the weft direction. So the strength in the warp direction, in the machine direction, is 50 kilonewton per meter. This is the ultimate strength, ultimate wide width tensile strength. Okay, ultimate wide width. You remember what is wide width? So wide width test we have studied. So from the wide width test, we got this ultimate tensile strength value, that is 50 kilonewton per meter. Okay, and the friction angle with granular soil of 24 degrees. Okay, the phi value is 24 degrees. Okay, and it is intended to be used in construction. Alright, so the friction angle, the granular soil that you are using for the construction, that is a what? There is a friction angle of 24 degrees. Is intended? Okay. Orientation of the geotextile is perpendicular to the wall face, and the edges are to be overlapped or soon to handle the weft direction. So in the like this it is placed, and this direction, in this direction it is shown like this, right? Obviously you have to sew the geotextile here like that. So that we will see later. Okay, we will see that. The factor of safety of 1.4 is to be used along with appropriate geotextile reduction factors. Okay, fine. Right. Okay, so a wide width test ultimate tensile strength value of the geotextile is given, and the friction angle of that geotextile, with the what, the friction angle of that geotextile with the soil, backfill soil, that friction angle, the interface friction angle between the soil and the geotextile, that is given as, given as 24 degrees. Okay, 24 degrees. Okay, so all this information is actually given to you. Now let us see how we shall solve it. Okay, so let us do step by step. Okay, so first what we will do, we will decide all the our what to say, the horizontal, this one, spacing and all, internal stability criteria, all those things we will use. First, this internal stability we are going to use. We are going to resolve the internal stability part first, and then later we will be doing the external stability, right? Because see, because to do the external stability analysis, you need to know how much length of geotextile you have put and all those things, right? So that is required. So that we will do later. The first what we will see that white is in it, or automatically it will get clear. Okay. First, what we need to do? First we need to do the internal, use the internal stability criteria to fix the spacing and the embedment length. Okay. So these were the main two internal stability criteria. The rupture will fix the spacing, and the what your overlap or the embedment length will be actually solved by will be decided by the pull out capacity, right? By the pull out capacity. So let us start. So A. So first what we need to do, we need to determine the horizontal pressure as a function of depth z. At the function of depth, we need to find out the horizontal pressure that will be acting. Okay. So first determine. Okay. So what is this? What do you want to do? Right? So what I said, first we are going to satisfy the internal stability criteria. The first internal stability criteria is our rupture. So to satisfy the rupture, it will be satisfied by what? The vertical spacing. Okay. And for that you need the horizontal pressure, right? So first what we will determine, what we will first we are going to determine ka, right? What is ka? The active earth pressure coefficient. Okay. So what is ka? Okay. So calculate this, how much it comes. Please calculate. Please try to do the problem with me also, along with me, else you will like lose the contact. If you keep on doing the problem with me, you will be more engaged with it, right? So try to solve the problem with me. Okay. Okay, so this will come out as 0.26. All right. Now next, what then what will be your horizontal pressure? So the active plus from the surcharge load. Okay. So here you can consider other factors also. Okay, seismic load also. Then you can consider the live load also. All these things. So as per your requirement, you can add whatever forces you want. Okay. So, but here for simplicity, we are considering this one. Into Z, right? What is this? K into Q. So we will get 0.26 times K into Z plus 0.26 times 10 is given, right? It's given 10 kPa. Okay, 10 kPa is 10 kPa is given to us, right? 10 kPa is given to us. So this will come out as 4, 5, 6, 8, 7, okay, so so remember this. Okay, we'll use it. So this we got. Okay, this we got 4.68 z plus 2.6 z. What is z? Z is the depth from the top. It is the depth, vertical depth. Okay, the top of the one to be got. Right now, see, the ultimate width width tensile strength is given to us, right? The ultimate width width tensile strength is given to us. Okay, the ultimate width width tensile strength is given to us. So what are we going to do? We are going to reduce it by some reduction factors to get the allowable tensile strength. Right? We'll reduce it by certain factors to get the allowable tensile strength. So the ultimate will get the allowable. So what is the allowable? The ultimate divided by certain factors. So factors: installation damage, reduction factor for installation damage, reduction factor for creep, and reduction factor for chemical biological damage. So I will just use the basic value. So this one will be 1.2 times 2.5 times 127. Okay, so this one will get us 50 by so the ultimate tensile strength is 50 kilonewton per meter, but we have used some reduction factors to reduce it to 1.2 or 13.2 kilonewton per meter. Okay. Now the load coming on each reinforcement, right? The load coming on each reinforcement is proportion what is proportional, or should be actually less than, right, the load coming on each reinforcement, right? So the load coming should be less than the uh, allowable strength of the reinforcement, isn't it? So this should be less than the T allow, isn't it? Why? To prevent rupture. So to prevent rupture, the load coming on each reinforcement should be less than T allow, right? Should be less than T allow. Now SV, which is the vertical spacing, times sigma h is nothing but T allow by some factor of safety, you can write. And what is SV into sigma h? That is the load that is getting transferred, load that is acting on the reinforcement. So you have reinforcement like this. So SV is the spacing of the reinforcement. So if you consider one reinforcement, so SV by 2 up and SV by 2 down. So this will be actually what this will be aiding to the uh, to to the load transfer this much area, right? So this sigma is, so see, this is the reinforcement, right? So it is varying something like this, it will be varying something like this, right? The sigma h. Now what we do, you take this much area SV, so up it's SV by 2, it's SV by 2. So what we are doing ultimately, we are just averaging it. Okay, we are averaging it. Okay, so that's and obviously the load coming should be less than the TLO. So what we are doing, we are using some factor of safety here. Okay, we are using some factor of safety. Okay, so what is spacing? Factor of safety. So now just put the values. What is T sigma h? Sigma h, right? You should have put sigma h, right? So this sigma h expression we can put here. Right, and the factor of safety you can take 1.4. Alright, this is the what? This is the expression for the vertical spacing. Now as you can clearly see, with the increase in z, with the increase in depth, what is happening? With the increase in depth, your spacing is actually will reduce, right? So if the denominator increases, the spacing is going to reduce, isn't it? So this is quite intuitive, right? This is quite intuitive. So with the increasing the depth, the spacing should reduce because the pressure is higher, the load is higher at the bottom layers, so the spacing is reducing. Now the task is that it's up to you how do you want to decide the spacing. So now see, now for what is the maximum depth of 6 meter wall we have to construct, the wall height of 6 meters we have to construct, isn't it? 6 meter high wall we have to construct. So what we can do now, let us see for z equal to 6 meter what SV will get. 13.2 divided by 4.68 times 6 2.60 times 0.4. So if you do this, you will get SV as 0.307 meter. So we can use 0.30 meter. Okay, so the bottommost layer of reinforcement that you are going to provide, we can use zero point 0.3 meter spacing reinforcement. Now the other reinforcement what you can do, so for each, so number of reinforcements and everything else, that is up to you. That is your choice. How much spacing you want to give, means how many layers you want to give, layers of reinforcement you want to give, all those things, these are at the designer's discretion, right? It is at your discretion. Okay, understood, right? So this is the minimum spacing that this is the maximum what to say, spacing below that, spacing below this 3.30 value is safe. Okay, now as we go up, the spacing requirement will be relaxed. That means the spacing is going to increase. That means that as we go up, we can use higher spacing, isn't it? So those adjustments you can do by yourselves. Okay, so those adjustments is completely up to you. How do you want to do? That is completely up to the designers. Okay, up to the designer's choice. So let us see now. By trial and error, for z equal to 3.3 meter, we get SVS 13.2 by it will come as 0.52. So you can use, so at 3.3 meter, the almost at the mid height of the wall, we can increase the spacing from 0.3 to 0.5 meter. All right, and now say, okay, so now how many layers you want to provide, it's completely up to you. How many layers of reinforcement you want to provide, that is completely up to you. That is completely your choice what you want to do. Okay, that is completely your choice what you want to do. Now see, let us provide total 6 meters we have to cover. Total 6 meters we have to cover. So let us, what we can do, 9 layers let us provide at 0.30 spacing. 9 layers at 0.30 spacing. So from here to here, how much will be covering? Hmm? So 9 layers if you provide at what to say, 0.3 meter spacing, then yeah, so then how much distance? So this much from here to here will be how much? 2.7 meter. Now remaining is how much? 6 minus 2.7. 6 minus 2.7. So that much. Now see, first we decided the 9 layers will provide with 0.3 spacing, right? Now next we have 3.3 meter above. Now how to distribute that? Now at 3.3 meters, so from here to here it's 3.3 meter. Now we already checked at 3.3 meter we can provide 0.5 meter spacing. So what we can do, we can provide 4 more layers, 4 layers at 0.5 meter spacing. Okay, so total how much have you covered? 9 into 0.3 plus 4 into 0.5, so 4.7 meters you have covered. So 1.3 meters it's remaining. So this remaining, so from, so remaining 1.3 meter, what we can do, we can provide 2 at 0.65 meter spacing. Now how to check, how to check if this 0.65 meter spacing, this 0.65 meter spacing is appropriate for that height or not? So we will check for z equal to 1.3 meter. What is s? 13.2 divided by 4.68 into 0.4. So this will come out as 1.0 meter. So we can use 0.65 meter spacing. Fine. That means safety is it is safe. The criteria is satisfied. Right. So this way you need to adjust the spacing. So it is as per now 9 at 0.3. You can provide 10 layers at 0.3 meter also. It is totally up to your choice. This readjustment that you are doing here, that readjustment is completely your up to you. Okay, so this readjustment is completely up to you. It is to be done at your own discretion. Okay, it is up to the designer choice, but you need to ensure that this safety is maintained. You need to check that whether the spacing you are providing, that is less than the calculated spacing or not. That you need to check whether the spacing that you have chosen, that is less than the calculated spacing or not. All right, now next, so I will draw the figure for you. So what we did, so total how many layers then? Total how many layers are we providing? 9 plus 4 plus 2, 15 layers, right? Total 15 layers we have decided that we will put. Okay, let me just draw. So this is the top surface. Okay, this is first layer, second layer, third layer. Okay, so let me number from down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 3, 4, So 9 layers at 300 mm spacing. What spacing? Obviously vertical spacing. Okay. Then we have 4 layers at okay. And at the end what we have 2 layers, right? So this is what we have decided. Okay, 9 layers at 300 mm spacing, 4 layers at 500 mm spacing, and 2 layers at 650 mm spacing. Alright, so this is how we have decided the distribution. Alright, done. So spacing first part is done. We have already solved the satisfied the first criteria, that is the rupture criteria. Now, second is to determine the length, and that length of the reinforcement, this length of the reinforcement, that will actually satisfy what? The pull out criteria. This length is going to satisfy the pull out criteria. Let us do. So this is the second part. Determine the length of the reinforcement layers. So if you recall, in the last previous session also we had discussed this thing, right? So how to do so? See, so say this is the wall of height h, and this is the active wedge. Right, this is the wall of height h, this is the active wedge. This one is whatever plus 5/2, and we are calculating at any, say this is one reinforcement at any depth z. Okay, at any depth z we are calculating. Now at any depth z, this distance let us call LR, and this distance is, you know, let us call embedment, like LE. Now this LR you can determine from the geometry. And what is that? H minus Z tan of 45 minus 5/2. So if we do, it will be 6. H is 6, right? So 6 minus Z tan of 45 minus 36/2. Okay, so 6 minus Z tan of 45 minus 36/2. Please do it. Please do. So it will come out as 0.509. All right, understood? Now, what is LE? If you can recall, what is LE? So LE is what? LE is the embedment length. That means the frictional resistance at this embedment region. The frictional resistance at the embedment region should be greater than the pull-out load that is coming. So we'll use that relation. So what is the load that is coming? Again, same, spacing into horizontal pressure times the factor of safety. Spacing times the horizontal pressure times the factor of safety, same as before. So what? Same as before, whatever we did previously. This is the horizontal load that is coming, and frictional resistance we get 2 C plus sigma z tan delta. C is the what? C is the cohesion, adhesion between the reinforcement and the soil. Gamma z you already know. Delta is the friction angle between the soil and the reinforcement, soil and the geotextile in this case. And why twice? Because the top layer and the bottom layer, both top surface and the bottom surface of both the surfaces of the reinforcement are contributing to the shear resistance, right, or the frictional resistance, isn't it? Right? Both the top and the bottom layers are both the top and the bottom surfaces of the reinforcement are contributing to the shear resistance. That's why you are using tool, right? So now we can just put all our desired, all the equation. This is the expression for sigma h, factor of safety 1.4 we can put, this given the question. To question is 0, we can consider 0 question. 18 into z into tan of 24. This is also given in the question. The interface angle between the geotextile and the soil the soil, this is also given. So we put. Now if we calculate, we'll get SV times 6.55z plus 3.64 by 16z, right? 16z, isn't it? How much? 2 into 8. Yeah, 16z. Okay, 16z. So what is the total length? Total length is LE plus LR, right? Total length is LE plus LR. So LR comes from the geometry. LR comes from the geometry, and our LE comes from the pull-out criteria, right? LE comes from the pull-out criteria. Okay, understood, right? Understood, right? So LE comes from the embedment, that is the from the pull-out criteria, and LR comes from the geometry, right? So total length is LE plus LR, correct? Done. So now you can see here this LE is a function of the depth and also the spacing. So also a function of the depth and also the spacing. So for that, what we'll do, we'll prepare it in a tabular format. Okay, we'll prepare it in a tabular format. How to prepare it in a tabular format? Let me show you. So what we'll do, we'll put layer number, then we have depth Z meters, then we have the vertical spacing as V meters, then we have LE, the embedment length that we are going to calculate at depth, particular depth for particular spacing, meter. What is the minimum that also we know? What is the minimum embedment depth by FHWA standard? By FHW, according to FHW, what is the minimum embedment length? The minimum embedment length is 1 meter, so that is 1 meter. So we'll see that if LE is less than LE minimum, we will take LE as 1 meter. Okay, and then we have LR, and then L calculated, and then we have L specified. We'll see that. What is L specified? What is L specified? We will see that. Okay. So layer 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Then what are the depths? 0.65, 1.30. Understood, right? So if you recall this, so from here we are measuring, right? Here we are measuring. So this is 0.65, then 6, 1.3, then 1.3 plus how much? 0.5, 1.8, like that you have to calculate. Understood? Understood, right? So from here to here 0.65, here to here, how much? from here to here 0.65, then from here to here 0.65 into 2, 1.3, from here to here 1.3 plus 0.5, 1.8. So like this we need to calculate for each year, right? So I will just write it down. Like this we need to fill it up, and then we have the spacing. Like this you need to fill it up. So what I will do, I will just stop the screen share from here. I will just share the, I will share the, share a Excel, okay, so that we can do that in Excel. It will be more helpful. Okay, I hope you can see the Excel sheet. I hope you can see the Excel sheet. Okay, I hope you can see the Excel sheet. So what we are going to do, we are just going to make a table. So layer number, then we have depth, set, meter, then we have SV meters, then we have LE meter, then we have LE meter, then we have LR meter, then we have L calculated, F L meter. What is L specified? What is L specified? We are going to see. Okay, what L specified is, what else specified is that we are going to see. Okay, what else specified is we are going to see that, right? I hope you understand. Okay, so write it properly. Okay, so layer number what, 15, 14, like that, 1. Okay, now what are the depths? 0.65, then 1.30, then what, 1.80, then 2.30, then 2.80, then 3.30, 3.60, 3.90. Okay, right? Understood? Next we have SV minimum, SV, whatever SV you can. So here 0.65 we have given, here 0.65 we have given, then 0.5, 0.5, point. Yeah, 4 layers we had given, right? Then 0.3, right? Now what was LE? What was LE? LE was equal to SV times. Okay. Okay. So you can see, you can see it very well. You can see it very well that uh, you can see it very well that all the LEs are less than the LE minimum. So what is LE minimum? LE minimum is 1 meter, 1 meter from where? LE minimum is 1 meter as specified by whom? As specified by Federal Highway Administration. Federal Highway Administration. So it is minimum. So LE is less than LE minimum. So if we take LE, LE is LE minimum. Okay, 1 meter you have to take. Okay. Now next we have to calculate LR. So LR is how much? 6 minus Z and 5 is to 9. This is LR. Okay, this is LR. So total is this plus this. Why you are taking LE minimum? Because all the LEs are less than 1. If this would have been higher than 1, then that higher value we would have taken. But since here this LE are less than LE minimum we are taking. Okay, so this is the total length of each of the reinforcement that we have considered. Now what we can do to just simplify the lengths that for construction purpose. So in the site it's easier to implement. So that in the site it is easier to implement. What we will do, we will uh, for all these three we are going to take 4 meters. Okay, for all these three we are going to take 4 meters. Okay, we are going to take 4 meters. Then just a second, yeah, and then the next from here to here, from, sorry, not 3, right? I did a mistake, I wrote for 4. This 3, let's take. Okay, the next from here to say how much? 2.7, right? Here what we can do, we can provide 3, so this one we can provide 3 here, 3 meter. All are larger than these values, so that we can do 3 meters we can provide, and the rest for this much we can provide 2 meter length. 2 meter. So this way you need to do the design. So just to see what we, for these three layers we specified 4 meter, then from this layer to this layer we specified 3 meter, and from this layer to this layer we specified the length as 2 meter. So just we simplified it just so that easily we can implement. Obviously higher length we have to specify so that our design is safe, right? So this is how we need to do it. Okay, this is how we need to do it. So what I will do, I will just copy it and paste it for you in the PowerPoint presentation. Okay, just copy and paste it in the PowerPoint presentation for you. Okay, just give me a second. Okay. Meanwhile, I will stop the screen share from here. Just a second, huh? Just copy. Okay. Okay, so this one is the final result. Okay, final result. All right, done. So this part is done. This part is this part is done. So next we have to do, we need to check for the overlap length. Okay, so two things we have done. This is the third thing, right? So two internal stability things we have completed. This is the third thing. Overlap. So see, say this is the wall, right? So this is the wall, and like this you are placing the geotextile, then so this direction the width will be less, right? So you need to use one more geotextile like this, overlap it, so this portion, this first portion will be overlapped, isn't it? This is rft1, say this is rft2, overlap. So that we have to do. It is similar to the this calculation whatever we are going to do now. This calculation is almost similar to what we did for the embedment length calculation, right? So here we will just one difference we will see, same as v into sigma h into fs, this much it's same. Here we will have 4 times ca plus, why 4? Because we have two overlap, one overlap, right? So it is overlap like this, overlap, right? So 1 2 3 4, four surfaces we have, four surfaces, so 4. Okay, as for in pull-out capacity we have one surface, so two is there. Here we have two surfaces, so we'll have 4. Okay, we'll have 4. Okay, so sv times again sigma h, you write, take 0. Okay, so this is the expression for L naught. Now we will say that for again we have to make a table and calculate L naught for each of the S, V and Z or what. I will say no. What we can do, just let us calculate for, so you can see here, if, okay, so if our Z is less, then L naught will be high. If the Z is less, then L naught will be high. So for less depth, let us check. For Z equal to 0.65 meter, it will be the highest. For Z highest, it will be the L naught will be the highest. Okay, for Z minimum, we will have L naught as the highest. So let us see. for this if we put for z equal to 0.65, SB is what, 0.65. Therefore if we put in this equation we will get L naught as 0.25 meters. Okay, but what we will use, as it is very less, we will use 1 meter of over 1 meter throughout. So minimum overlap, minimum this overlap you are using 1 meter again minimum. Okay, so the maximum overlap will be coming at the top for minimum Z. So if you check that it is coming at 0.25, so if we put 1 meter it will cover the whole height. Okay, it will be sufficient for the whole height. Right, now let us draw the final figure whatever we have decided. So this is our design, right? This is our design. Lower layers, your width length is 2 meter, then middle is 3 meter length, and we have 4 meter length. Okay, so let us see. Let me draw. Okay, so let me just draw it like that only. Fifteen, 14. It's a bit difficult to draw. Just a second. 14, 13, 12. So like this it's there. Okay, now if I mark say 1 2 3 4 5 6 7 8 9 10 12 13 14 15. Now top two layers is 15th and 14th layer. What is the length? What is the length? 4 meter. Okay, not 15th, 14th and 13th layer. 15th, 14th and 13th layer we have 4 meter length. So here here have 4 meters. Next, layer 12, layer 12 to layer how much, 8, we have 3 meter. So layer 12 to layer 8 we have this 3 meter. Okay, and the below layers we have this from here to here we have 2 meter. Okay, so these are by how we have distributed the length, okay, along the wall. Now the properties of the, now what, now we are proceeding towards the overall stability, external stability check. So internal stability we have already finished. Now what we are going to do, we are going to the external stability checks. All right, so we have the backfill soil. So what is the backfill soil? The backfill soil properties gamma F15 and foundation soil This is the addition. Okay, so these are what we have in our hand. These 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 are the things that we have. Now what I will be doing is that I won't be considering the size, as I said in the beginning only, the seismic forces and all these things I won't be considering. But what you can do is you can redo all these problems again by yourself, considering live load, seismic forces and all those things in whatever way it is been taught in the class by Professor Rajagopal. All those methods, by using those things, whatever however steps he has shown you, by following the Federal Highway Administration guidelines how to do that, you can resolve these problems again by yourselves by considering all those things. And these problems actually I'm showing you like basic, the main concept, the main base, to just so that the main concept, the basic concept is clear. For that I am showing you, okay, how to do that. Okay, now see, now here see, now this is the actually, so here some PA will be acting, PA, it will be acting at an angle delta as you are considering rough. So for that what you have to do, you have to first calculate the Ka, 1 minus sine 34 by 1 plus gamma at 0.28. Okay, therefore PA is, so see, you can see here, right? Simple expressions have other things like live load, dead load, all these things I'm not considering. But please redo these problems by considering all those things. Okay, I'm just doing in a normal way. Okay. Just so that the basic concepts are clear, we are solving it in the most simplest. We are considering only the simple things. Okay, so PA is acting like that, so PA will be having two components, PA cos and PA sin delta. So what is PA cos delta? Like PA sin delta is, and its delta is actually taken equal to 5 here. Okay, now factor of safety in overturning is equal to, I will explain. Okay, w1 x1 plus w2 x2 plus w3 x3 plus PA sin delta into 4 by PA cos delta into 2. Now let me show you. Now see, what are W1, W2 and W3? W1, W2 and W3 are the weights of this block, this block, let me color it. Okay, it is the weight of this block. This is the weight of W1. Now what is W2? W2 is the weight of this block. Okay, and W3 is the, obviously W3 is the weight of this block. Okay, so this is how we divide W1, W2, W3. Now what are we doing actually? What are we going to do? We are taking the moments about this point. Okay, here. So x1 is the distance of here, from here to here, x2 is the distance from here to this point, and x3 is the distance from here to this point. Okay, so like this we are doing. So now What is W1? What will be W1? W1 is nothing but the area of this yellow triangle. 6 meter is the height, right? Total height is 6 meter. 6 meter times this width. This is how much? This is 2 meters. 6 into
2 meter.
2 into 18. 6 into 2 into 18. And what is x1? X1 is 2 is the width, so 1 2 by 2, right? Then plus what is W2? W2 is how much? This width. This width is how much?
1
1
meter.
meter into this height from here to here. This height. What is this height? This height is
Minus.
how much? 6 minus uh, 7 into 7 layers are there below. 6 minus 7 into 6 minus 7 into point 3. So 3.9. Okay, so this is 3.9 meter and this is 6 meters total. This is 3.9 meters. This height from here to here it is 3.9 meter. Okay, 3.9 meter. So 3.9 times 1, because this width is 1, this width is 1, times 18 times 2 plus 1 by 2, right? 2 plus 1 by 2 is the x3. 2 plus 1 by 2. Now last for w3. W3 is this height. This height means how many layers? 3 layers are there, so 3 into 0.65 is a 0.6 rest, right? So see, this is going to be 1.8, right? So this is 1.8. 6.65 into 2 plus 0.5, so 1.8. So from here to here it is 1.8 meters. So that we are taking. So 1.8 times this is how much? This is again 1 meter. So 1.8 times 1 times 18 plus plus
2 plus
here
1 plus
it's
2
4.
plus 1 plus 0.5 by 2.
Cannot hear. You are not audible. Please try to speak louder.
It's okay, carry on, sir.
So this is 4. 4 minus 3, 3.5. Okay. 3.5 plus PA sine delta into 4. Why 4? Because from here to here it is 4. Now these are the disturbing moments, right? What is the disturbing moment? PA cos delta times 2. Why 2? Because it is acting at a height of h by 3. 6 by 3 is equal to 2. Okay. So this one if you calculate, you will get the factor of safety as 4.7, which is greater than 2. So acceptable. Now next is the factor of safety in sliding. So similarly, you will calculate. I will just write it down. Ca into L. Ca into L, the addition between the geosynthetic at the bottommost layer, addition between the geosynthetic at the bottommost layer with the foundation soil. Okay, addition is the addition between the geosynthetic at the bottommost layer with the foundation soil. So Ca into length, and L will be how much? 2 meters, because that is in contact with the foundation soil, plus W1 plus W2 plus W3 plus here sine delta by here. Please take care of the units. So if the units are correct, there won't be mistake. People generally make mistake here with the units, whether it is kilometer per meter or kilometer meter per meter. All these things please consider. Okay, take care. Times L. So we are taking the average here. Okay, average force. Okay, so this times PA cos delta. Okay, so we'll get 16 into 2 plus 216 plus 72. This will come out as 2.1, which is greater than 1.5, so safe. Okay, so slide overturning check is done, sliding check is done, like sliding check is done, overturning check is done. Last, which one is remaining? The last external stability check, that is 7. Which one is that? That is the bearing, right? Bearing capacity check. So the P ultimate bearing capacity. So this one here, just I am writing the normal Terzaghi's formula, plus whenever you are calculating, please use your IS code formula. Okay. 18.5 to 2.65. What is the P acting? Acting is the weight of the total block. 18 into 6 plus 10 is the surcharge, it is there, so 118. Okay. Okay, so what I will say, this solution is done according to corners. Okay, however it is done in whatever way it is done in the book by Robert M. Cornard, so in that way I have done this solution. But whenever you do, so what I suggest is please redo this. Okay, please redo things all these things using whatever method has been taught in the main lecture class. Okay, by taking seismic forces and all those things, how by calculating the vertical pressure using sigma vertical by rv by b minus 2ic, all those things, use all those steps to redo the problem. Just you can see this problem to just clear the basic concepts, what is happening. But then I suggest this, please redo. Okay, please resolve the problem using the method discussed in main lectures by Professor. Okay, please resolve all these things. Okay, so done. So next, this one, for this one you can use Terzaghi. Terzaghi is used. You should use the IS code, and this calculation is also not properly done. This one you can use this sigma v by sorry rv by b minus 2ic, all these things. Then here also seismic loads and all, it is not uh, we can include seismic load, live load, all those things you can include. So like that you can do. Okay, so done. Now next problem. So this is going to be the last problem for today. Okay, so next class also we'll be solving some more stuff. So as it takes time, very much time to solve these problems, we cannot solve too many, but still we'll see how many we can do, how much we can do actually. Okay, see how much we can do. Now see, this is a typical section of a cantilever wall with backfill reinforced with metal strips. So here metal strips are used instead of geosynthetic. Okay, typical section of a retaining wall with backfill reinforced with metal strips is shown in the figure below. The following data are available. H is equal to 9 meter, means the total height of the wall is 9 meter. Then B is 100 mm, means the width of the strips. So these are strips like this. Okay, small strips of reinforcement are used. Okay, small strips of reinforcement. The width of each strip is 100 mm. Okay, the thickness of each strip is 5 mm. Fy, this is the yield strength of the steel strip is 240 MPa. Factor of safety for the FS is 1.67. FS on soil friction is 1.5. Friction angle of soil is given. Unit weight is given. Okay, 25 degree. All those things are given. Okay. Now SV by SH. Here see, as we are using strips, as we are using strips for construction here, previously we just had in the case of geosynthetics we just have vertical spacing, right? The horizontal spacing was irrelevant because the geosynthetic will be covering everything. But when you're using strips, geosynthetic steel strips, at that time we have to consider the horizontal spacing also. The horizontal spacing and both the vertical spacing both will be coming into action here. Here, the SV times SH is given as 1 into 1 meter. Okay. Required, what are we required to find? LE and L and LE at varying depths, the largest tension in the strip, the allowable tension in the strip, and the check for external stability. So let us see. Let us start the problem step by step. We will solve. Okay. Slowly we are going to solve. Now see again. Similar thing we will do. What is sigma H? Gamma Z Ka. Right, gamma z is the vertical and times k is the horizontal pressure. Now what this problem actually we are going to solve in a little bit different way than the first problem. Okay, not like similar, not we are going to solve in some little bit atypical way. Okay, atypical, like a little bit different from what how in what way we solved the previous problem. Okay, a little bit different we are going to solve this. Just give me 1 second. Okay, so this one we have. Now see, now what is the load on each reinforcement? Nothing but the horizontal pressure times the SV times SH, right, times SB times SH. So that we are going to do the load on reinforcement is nothing but SH. Now 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 therefore T is nothing but sigma is, so gamma is 17.5, it is given. Z will keep Z, Z is the depth, times Ka 1 minus sine 30. How much it's given? 36 or 35 d? 36 by 1 plus sine 6 times SB into SH is given 1 by 1. Okay, here already it's given. Already the spacing they have given. Okay, just you have to check various things. This is not a design problem. This is more of a check problem. Okay, check problem. You have to check. Previous problem was complete design. From scratch you are designing. But here they have given the spacing, all these things. They have given the design. You need to check. Okay, you check various parameters. So this one will come as 4.55 Z kilonewton per strip. Okay, then what is LE? Similar to the previous one, factor of safety times T, that is a tension coming or the load coming on each reinforcement, divided by twice gamma Z B tan delta. B is the width. Okay, B is the width of the reinforcement here. The factor of safety is 1.5 times T, 4.55 Z times 2, 17.5 times Z times B is 100 mm, width of the reinforcement 100 mm, so 0.1 times tan delta is given as 24. Okay, so z z it will cancel out, right? So you are seeing that early here the embedment length is independent of z. The embedment length is fixed, it is independent of z. Okay, so we'll get fixed value. So here the embedment length is a fixed value. Okay, okay. So the load of the coming onto the reinforcement, that load we are equating, we are what we are doing, we are equating with the frictional resistance. The load coming on in the reinforcement, that you are equating with the frictional resistance. From here there we can get the pull out capacity. From this is the pull out thing check we are doing, right? So from this we can get the embedment length. So here we are seeing the embedment length is independent of z, independent of the depth. It is coming at 4.14 meter. Okay, now let us see. Now if you see the image, you can see 9 layers, 9 layers of, see, 9 layers of the steel strips are given, used. 9 layers of steel strips are given. Okay, 9 layers of steel strips are given. Now what is the tension or the tensile or the load that is coming on each strip? The load coming on each strip is 4.55 times z. Load coming on each strip is 4.55 times z. So what will be the total load? What will be the total load that is taken by totally? Well, totally how much load the strips are taking? That how to do? How to do? See. So say for top strip, it is taking 4.55 times 0.5. 0.5 is the height. For the next strip, it is taking 4.55 times 0.5 plus how much? How much is the spacing? 1.5. Oh, sorry, 1. So 4.55 times 1.5. Understood, right? So here to here it's 0.5. Here to here it's 1.5. Here to here it is 2. 2.5. Here to here it is 3.5. Isn't it? So what are we doing? So 4.55 times each z we have to do, so that we can get the total load taken by the total reinforcement. Right, so that you are calculating. Okay, that you are calculating. So summation t is what? Summation 4.55 z. So 4.55 summation z. So 4.55, 0.5 plus 1.5 plus 2.5 plus 3.5 plus, so all layers are to 1 meter apart. That's the top and the bottom layer, these are at 0.5. Okay, spacing from the ground and from the top level surface. Okay, that's all. Other all the layers are 1 meter interval. It is given to us, this design is given to us. This one will come out as, this much is the total load that is transferred to the total reinforcement. Totally, all the reinforcements together, all the reinforcements together are taking this much load, 184.27. All the how many reinforcements are there? All the nine layers of reinforcement together are taking this much 184.27 amount of load. Now what we have to check? We have to check that whether this load is coming equal to the load from the active thrust. So what is active thrust? Half sigma k a h square So half into 17.5 times 0.26 times 9 square. So this will come out as 184.3 per meter. So you can see that that means what, whatever lateral earth pressure that is coming, that is taken by the total all the strips. Fine. So it is fine. Our design has been done correctly. That means okay. Now next part. Now but each layer, okay, each layer. Now see the maximum load out of this uh, the maximum load will be taken by the bottommost reinforcement. The reinforcement that is at the bottommost layer, because that is taking the maximum load, maximum pressure that is taking the maximum pressure. So the bottommost reinforcement is taking the maximum load, isn't it? The bottommost reinforcement is taking the maximum load. So for that we have sigma z ka s v s h, right? So sigma is 17.5. Like what is z for the bottommost reinforcement? 8.5, right? 8.5, isn't it? From here to here it is 8.5 meter, isn't it? So 8.5, so 17.5 times 8.5 z. Ka you already know, sv you already know, sh you already know. So this will come out as 38.68 per meter. So out of 184.27 kilonewton per meter, kilonewton, that is taken by out of 184.27, 38.68 is taken alone by the bottommost reinforcement, bottom layer of reinforcement. 38.68 is taken alone by the bottom layer of reinforcement. Okay. Now, why are we doing this? Why are we doing this? So we are finding the maximum load that each layer of reinforcement is taking. The maximum load that is transferred to each layer of reinforcement, so that we can check whether the allowable strength of the reinforcement is greater than this much of this value or not. This is our target. We are checking. So we are checking that the maximum load that is coming to the reinforcement is is lesser than the strength of the reinforcement or not. The maximum load that is coming to the reinforcement, is lesser than the strength of the reinforcement or not. I am again repeating, the maximum load that is coming to the reinforcement, it is less than the tensile strength or the yield strength of the reinforcement or not. Okay, so that's why we calculated the maximum load that will be coming to any reinforcement, that is the bottommost layer. So we calculated this. Now what is the allowable strength? Allowable strength is nothing but F allowable. F yield is given to us, yield strength. From that allowable strength you have to find. Allowable times thickness times width. So F allowable is nothing but 240 MPa. It's given. It's the yield that I will divide by the factor of safety or the reduction factor to get the allowable. 3 kilonewton per meter square. So therefore T allowable will be nothing but, what is the thickness? 5 mm. And what is the width? 100 mm. What have I written? 3. So this if we do, this if we calculate, you will get as 72 kilonewton. Now you can see 72 kilonewton per meter is obviously greater than 38.68 kilonewton. Okay, 38.68 kilonewton. Hence it is okay, and it is okay, right? Now next, so this is done. Now next what you have to do, we have to check our length. You have to calculate the length. So how to calculate the length of the reinforcement? It is nothing but LR plus LE. So LR is from the geometry. And what is the embedment length? This already we calculated. This is fixed value, 0.14. Isn't it? 4.14. Okay, so with this what you can do, you can check, we can check if the length of the reinforcement that is given here, it is correct or not, it is correct or not, you can check. Okay, you can check. So how we can do, let us if you want to check, what you can do for the topmost layer. See, for the topmost layer, if I want to calculate, let me put z is equal to 0.5. So for z is equal to 0.5, I will get L as how much? What is h? H is 9 meter. This is 9 meter. So 9 minus 0.5 times 10, 45 minus 36 by 2 plus 4.14. It is coming as 8.5 meters, 8.47 meter. Now check how much they have given here. They have given 8.5. Okay, so that's why they have given 8.5 meters. Okay, you can see 3.8 plus not 3, this one is irrelevant. So this maximum length you are seeing, that's why they have given us 8.5 meter. Okay, that's why they have given us 8.5 meter. Okay, why 8.5 meter, you can check from here. So for z equal to, this one will be 9 minus 0 0.5, 10, 45 minus 2 plus 4.14 by 8.47 meter. Okay, that's why they have provided 8.5 meter. Okay, so done. So these are the next thing that you have to do is the sliding check and all this stuff. Now, what is factor of safety against sliding? Factor of safety resisting by factor of safety disturbing. A factor of safety resisting, factor of safety is nothing but weight, the frictional resistance at the base, frictional resistance at the base. Okay, frictional resistance at this place, frictional resistance at this place, this interface, the frictional resistance, right? So what is that? That is nothing but W10 delta. Okay, it is nothing but 4.5 plus 8.5 by 2 times 17.5 times 9 times 10. So what they have done, they have calculated this one. See, here to here it's 4.5, here to here it's 8.5, right? So what they have done, they have calculated the average 4.5 plus 8.5. Okay, the average width. Okay, average width they have calculated. Average width times the height, it is 9 meters, times the so unit weight times the 10 times 1036. It is the interface friction. Okay, interface friction. Okay, like this they have done. Okay, like this they have done. So I will just show you, just a second. So what they have done is, so what they have done, they have divided it into, so they have divided the whole part into two things. One rectangle, like you see, it is 4.5 to here, right? One rectangle and one, say, triangle, like this, one triangle. Okay, like this they have divided it, that they have calculated. So this, they have taken the average width, they have taken the width of the rectangle. But you if you want, you can do like the previous fashion also. In what way we have done, so just we can you can take this edge first, then this first, like this also, like this you can do. Okay, like this you can do, that will be better. But what in this book advanced notation, in that solution whatever I have, what they have done is that they have taken the average. Okay, average they have taken and then they have done. So this one comes out as 744 kilonewton, and our PA is 184.28 kilonewton. So factor of safety in sliding, is 744 by 184.28. It was 4, which is 1.5. So okay. Now next is the overturning. Overturning, the resisting moment by overturning moment. Resisting moment, what they have done, 4.59. Understood, right? So for the first case, what they have done, for the first case, what they have done, they have considered this trapezium. Okay, this trapezium they have considered, and this area they have calculated for the weight here. Where? Here. Okay, in this part. Okay, in this part. But when they have calculated for the overtime, but see, this you might get confused with this, but what I suggest, you don't calculate it like this. Whatever I showed in the previous problem, you follow those steps and that way calculate. Okay. So in this case, while calculating the resisting moment, what they have done, they have considered this. They have considered this rectangle they have considered, and this triangle they have considered. Like this they have considered while calculating the moment, resisting moment. But while calculating this other thing, they have considered a different way. So different way. This is very confusing. I understand. So it's better you calculate it the way I have shown in the previous problem. Okay. But here, just for the sake of completion, I will write it. So this is the weight of that rectangular part, and this is the lever arm 4.5 by 2. Then we have calculated the weight of this triangular region. Okay. Half into 9 is the height into 8.5 minus 4.5 times 4.5 plus 4 by 3. Okay. Into 17.5. So like this they have calculated. This is 4.5. This is 1. This is 2. So this is for 1. This is for 2. Okay. This will come out as 3432 kilonewton. And what is the overturning moment? PA times H by 3. So vector safety in overturning is 3432 divided by 553. Okay. See. Okay. See. So this is how we need to solve the problem. Okay, this second problem was not a design problem. The second problem was just a, what to say, it was just a basic check kind of thing, check of design check kind of thing. First problem was complete design problem where from scratch we design. Okay, and so let us just see the first problem once again. Just we will revise for 2 minutes. So this was our question. we are asked we were asked to we are asked to design a wrap around geotextile wall. Okay, geotextile wall. So wrap around geotextile wall. So first what we did, we determined the horizontal pressure at any depth. That we determined the horizontal pressure at any depth we calculated. Okay, first we calculated the horizontal pressure at any depth, which is a function of z depth. Then T allowable we calculated T allowable. T allowable we calculated from the ultimate by using reduction factor. Then we use the rupture criteria to calculate the spacing. The vertical spacing actually satisfies the rupture criteria. Done. Then next is the length. The length. So we use rupture criteria, we fix the spacing. Then we chose the spacing as per our requirement. So choosing the spacing, is to the is at the discretion of the designer, but you should always make sure that it is safe. Okay, you should always calculate and check that whether it is lesser than the calculated SV or not. Okay, then this one, this is the number of layers and spacings that we decided. Then the next step was to determine the length of reinforcement, and for that we have to satisfy the pull out criteria. So that we did, we got the L. Then so this table we formed, this table then I should read it in Excel for you, so that easily we can do the calculation, and then we specified this length for the length of the reinforcement. Okay, and then we check for the overlap length. So the third internal stability criteria was the overlap. So proper overlap between the reinforcement should be there. So we checked it, and the maximum overlap will always be required in the topmost layer. There we check that 0.25 meter is required, but we will always use 1 meter as the minimum overlap length. So 1 meter we decided we will provide overlap of throughout the height. Done. So this was our final design. So this is what we finally decided, so that we will do. This is what our wall will look like, and then after that we solve the external stability, checked for the external stability. So this was our overturning check, then sliding check, all these things you can do, and the bearing check. Okay, and what I suggested was that you include whatever courses that are discussed in the class, in the main class, like the seismic forces, live load, all those things, and solve all these things by IS, using IS code, all these things using IS code. Then your federal highway administration, all these codes, you use this code, use those codes, and then you resolve these problems. Okay. Okay, so done. So with this we will end today's session, and our next session will be on the 7th of September 2024, Saturday, from 6 p.m. to 8 p.m. So 25th we won't be having any class. The 25th class is preponed to today, we did it today. And 1st September class, the session which was going to be held on 1st of September, that we have postponed to 7th of September. Okay, so with this we will end today's session, and let us meet on the 7th of September from 6 p.m. to 8 p.m. We will obviously getting reminders from the NPTEL team, so please keep an eye on the on your registered emails. The NPTEL team regularly gives you some updates, right? So I suggest that you keep an eye there, have a notice there. And that's all for today's session, and please resolve the problems again, as I said again and again. Resolve the problems, solve whatever problems has been taught in the main lecture classes. Many problems were solved, those problems also you solve, these problems also you solved again. So everything you do. And if you have any doubt, please feel free to contact me. And one more thing is that please try to follow, you can follow this book, as I said, Geosynthetics and Reinforced Soil Structures by Professor Robert Corner, that Robert M. Corner, that you can follow. Okay, so with this we will end today's session, and if you have any doubt, please feel free to contact me, and thank you for attending.
Thank you, Ashish.
Thank you.
Thank you.
Thank you.